Today we're looking at a fascinating paper called Inference-time PhysicsIQ of video generative models with latent world models. This one's from researchers at Metafair, Oxford, and Mila.
Right, and it tackles a problem that anyone who's played with video gen models has seen.
Absolutely. So for our 1-minute overview, state-of-the-art models, think Sora, Gen 3, the ones we're seeing in early 2026. They're visually stunning, but they're physically pretty dumb.
That's putting it mildly. They hallucinate motion, things just vanish, conservation of mass is more of a suggestion.
Exactly. So this paper introduces a system they call WMReward. And the key idea is, instead of retraining the whole giant model, they treat physics as an alignment problem you solve at inference time.
Which is a huge deal. No more multi-million-dollar training runs to fix one specific problem.
Right. They use what's called a latent world model, specifically VJH2, to basically act as a referee while the video is being made.
And the core metric is surprise. If the world model is surprised by what happens next in the video, the physics is probably wrong.
And they use that surprise score to steer the whole diffusion process. The result, it won first place in the ICCV 2025 Perception Test PhysicsIQ Challenge.
Yeah, a score of 62.64%. I mean, that's a massive leap over the previous baselines and really importantly over the VLM-based approaches.
It's a really interesting pivot, isn't it? From training time fixes to these smarter inference time solutions.
It is. It suggests we can maybe fix these models without, spending another $100 million on training compute.
Exactly. And that is the hook. Okay, so let's back up a bit and really set the scene. As we said, it's January 2026. We've got these incredible models like MDI-1 and VLDM.
Beautiful outputs. The pixels, the textures, the lighting. It can be photorealistic if you just look at a single frame.
But the second you hit play, that illusion shatters. The physics engine, if you can even call it that, just completely falls apart. Why is this still such a hard problem?
It really comes down to the fundamental training objective of these models. Broadly speaking, they're trained to minimize pixel reconstruction error.
So they're just trying to match pixels from the training data.
Precisely. They get incredibly good at learning the statistical distribution of textures and light. They're advanced mimics. They know what water looks like. It's shiny, it's reflective, it moves, but they haven't internalized the deep causal physical laws behind it.
So they know the texture of water, but not the viscosity.
That's the perfect way to put it. They have no inherent concept of gravity or fluid dynamics or rigid body collisions. They're just learning correlations, not causality.
So when a ball hits a table, it's not calculating a bounce based on physics.
No, it's just hallucinating what a ball-table interaction usually looks like from a pixel perspective based on all the videos it's seen. And, well, often that means the ball just kind of vanishes or morphs into the table.
It's the ultimate style over substance problem. But the core hypothesis of this paper is actually pretty optimistic, right? They're not saying the models are fundamentally broken.
No, quite the opposite, actually. The researchers posit that physically plausible videos, the correct videos, they do exist within the model's learned manifold.
So the model can generate it.
It can. The probability distribution of the model contains the correct physics. It is capable of generating a video where the ball falls correctly. It's just that the standard sampling methods, the way we asked the model to generate a video, they aren't finding those specific paths.
They're getting lost.
Yeah, they're getting lost in the much larger sea of visually correct but physically wrong options.
So the needle's in the haystack. We just need a better magnet to find it. Now, people have tried to fix this before. I know vision language models, VLMs, were a popular idea for a while.
Right. There's been a lot of work trying to use this sort of system 2 thinking, where you ask a model like Quinn or GPT-4v, hey, is this video physically accurate?
And it didn't work so well.
No. And as we'll see in the benchmarks later, that approach is surprisingly ineffective. It turns out text-centric models just don't have the granular, intuitive feel for spatiotemporal dynamics.
So if you want to fix physics, you need a physics engine, not a language engine.
Exactly. And that's the pivot in this paper. They move fully to test-time compute, using a specialized latent world model.
Okay, let's dig into that judge then. They call the system WMReward, but the engine driving it is something called VJP2. What is that, and why is it better at this than a VLM?
So VJP stands for Video Joint Embedding Predictive Architecture. The really critical distinction here is that VJP does not predict pixels.
Okay.
It predicts latent representations. When a normal diffusion model is generating a video, it's obsessing over every single pixel value. The RGB, the lighting, the noise. VJPA works in a much more compressed, abstract, latent space.
And why does that matter for physics? Why is latent better than pixel here?
Because by working in that latent space, the model naturally filters out all the high-frequency noise. It learns to ignore things like lighting jitter or tiny texture fluctuations or camera grain.
So it's not getting distracted by the superficial details.
Right. It focuses on the structural dynamics. It pays attention to how objects move, their trajectories, how they disappear and reappear, and how they interact in space. It's looking at the bones of the video, not the skin.
That's a great analogy. If you're trying to judge a foul in a football match, you're looking at the players' bodies and the ball, not the brand logo on their jersey.
Exactly.
So how does it actually judge the video then? You mentioned the surprise score. Walk us through that mechanism.
It uses a sliding window approach. So imagine you have a video sequence being generated. You take a chunk of frames, say the first few seconds, and you call that the context.
Okay, the setup.
You feed that context into the world model, into VJG2. The model then predicts the embedding, the latent representation of the future frames based on that context. It's effectively saying, okay, given that the ball is rolling towards the edge of the table, I predict the next latent state is going to look like the ball falling.
So it's actively forecasting. It's running its own little internal simulation of what should happen next.
Exactly. And then the clever part is they take the actual future frames the video model generated, encode them into the same latent space, and they just compare the two embeddings.
With cosine similarity, I saw.
Right. If the similarity is high, the world model says, yep, that matches my prediction. Low surprise. Good physics.
And if the similarity is low,
then the world model is surprised. It's going, wait a minute, the ball just floated upwards. That breaks my prediction. And that translates to a high surprise score.
which you then treat as a low reward.
You got it. You want to maximize the similarity, which means minimizing the surprise.
That's so intuitive. It's like having a little physics teacher watching over the model's shoulder, just raising an eyebrow whenever something weird happens. But having a score is one thing. How do they use it to actually change the video? You can't just shout wrong at a diffusion model.
Well, you technically can if you do it mathematically. The paper explores 3 sampling strategies to actually leverage this score. The first and simplest is called best of n, or BON.
Which sounds like brute force, basically.
It is, in a way. You generate n independent candidates. Let's say 16 different versions of the same video prompt, starting from different noise seeds. You then run all 16 of them through the WMReward filter, pick the one with the best physics score, and just discard the other 15.
Simple, gradient-free.
Yeah.
But it sounds computationally expensive. Generating 16 full videos just to keep one seems like a lot of wasted GPU time.
It is. It's very expensive. And that's why they also looked at a method called guidance, which is denoted by that little nabla or nabla symbol.
Right.
Because the WMReward function is differentiable, you can calculate the gradient of the reward with respect to the video. They can inject the signal directly back into the diffusion process itself.
This is where they use Tweedy's formula, right?
Yeah.
I saw that in the methodology section.
Correct. They use an approximation with Tweedy's formula. And without getting too deep in the calculus, it basically lets them calculate a nudge at each step of the denoising process. So they aren't just waiting until the end to judge the video. They are actively steering the noise toward regions of the latent space that have higher physical plausibility.
So best of n is generate many, pick one, and guidance is more like steer one video while it's being made.
Right.
And the winning strategy was a mix of both.
Yes, the Nobel plus Bone strategy was the clear winner. It turns out the methods are really complementary. You use the guidance to generate better initial candidates, so your pool of 16 videos is already much better. And then you use best of n to pick the absolute best one from that higher quality group.
And that makes a lot of sense. And they found something really significant about compute scaling here. We always talk about scaling laws for training, but this is different.
Yes, and this is a crucial takeaway. They found that the physics quality scales directly with the search space. If you increase the number of particles, the n in best of n, the physics IQ score, goes up reliably.
So you can literally buy better physics at inference time just by throwing more compute at the search problem.
You can. We might be entering an era where inference-time compute is just as valuable, if not more so, than the raw parameter count of the model.
That is a massive shift in mindset. It implies that a smaller model with more thinking time could potentially outperform a giant model that's just, spitting out the first thing it thinks of.
Exactly. It's the system 2 transition for generative video. Slower, more deliberate, and more accurate.
Okay, let's get into the hard numbers. They entered this ICCV 2025 Perception Test PhysicsIQ challenge. How did they actually do?
They crushed it. They took first place, achieving a final score of 62.64% in the video-to-video setting.
And what was the baseline? Give us some context for that number.
So the previous baseline, using the MAGI-1 model alone, was hovering around 55%. They beat it by nearly 7%. In the world of competitive benchmarks, a 7% jump isn't just an improvement, it's like a generational leap.
That's huge. And they compared this against other reward signals too, right? You mentioned the VLMs didn't do so well.
They did a very rigorous comparison. They tried using video MAE, which is another method that uses pixel-based surprise, and they tried QuenVL, which is a big vision language model. And the results for Quen were, well, they were damning.
How bad was it?
The VLM-based rewards performed at near chance level. Basically, random guessing.
That is wild. You would think a massive, powerful model like Quen could look at a video and just tell you, that looks wrong.
You would think so.
Yeah.
But it turns out that these text-centric VLMs are trained to describe content. There is a cat, there is a ball. They're not trained to judge the subtle derivatives of motion over time. They lack that intuitive physics engine that a latent world model like VGP have been explicitly trained to develop.
So a VLM sees a still image of a ball in the air and just says ball.
Right. Whereas VJP sees the trajectory and implicitly understands ball moving downwards at roughly 9.8 meters per second squared. This paper pretty definitively proves that for this kind of problem, you need a model trained on spatiotemporal prediction, not just image-text pairs.
That's such a critical distinction. It means we can't just throw LLMs at every single problem and expect them to work. Did they run a human study as well?
They did, just to make sure the metrics weren't leading them astray. And human annotators preferred the WMReward aligned videos with an 11.4% higher win rate for physics plausibility compared to the baseline. So it confirms the numbers match what people actually see.
Now, one concern with these steering methods is always that you might break something else. You fix the physics, but suddenly the video gets all grainy or the colors are weird because you're forcing the model into a strange corner of the latent space. Did that happen here?
That's what's so interesting, though. The V-bench scores, which measure perceptual quality, did not degrade at all. In fact, aligning to physics actually reduced certain artifacts, like temporal flickering.
Wait, explain that. Why would better physics mean less flickering?
Well, think about what flickering actually is, physically. It's an object popping in and out of existence, or its texture changing erratically from one frame to the next. That is a violation of physics, specifically object permanence and temporal consistency.
I see.
By enforcing physical laws, you inadvertently force the model to be more temporally consistent. If the physics engine says the cup cannot just disappear, the video generator stops making the cup flicker, so the visual quality can actually improve.
I want to visualize this for the listener. We've talked a lot about scores and gradients. What are the actual qualitative wins? What does a WMReward video look like compared to a baseline one?
The paper has some really striking examples. Fluid dynamics is a huge one. There's a comparison of ketchup being poured from a bottle.
Ketchup is notoriously difficult, right? It's a non-Newtonian fluid.
Exactly. And in the baseline MDI-1 video, it just looks like red water. It's too thin, it splashes everywhere, it flows way too fast. With WMReward, the viscosity looks correct. It moves like a thick fluid should, it globs, it piles up on the plate.
Wow. That's a huge win for a general purpose model. What else?
Another great one is buoyancy. They show a rubber duck being dropped into liquid. The baseline model often has the duck just clipping through the water or sinking like a rock. It doesn't really interact with the surface.
Right.
The aligned model shows the duck hitting the surface, displacing the water, creating realistic ripples, and then bobbing and floating correctly.
And rigid bodies.
Dominoes. The baseline is a complete mess. The dominoes often just randomly collapse or, even worse, merge into each other like they're made of ghost matter. The WMReward version respects the chain reaction. One falls, hits the next, momentum transfers, and they fall down in a perfect sequence.
It sounds almost like magic, but every method has its limits, its breaking point. What's this exploding balloon problem they mentioned in the paper?
This is a really fascinating limitation. The model struggles with abrupt discontinuous events. The main examples they give are a balloon popping or a match suddenly igniting.
Why does it fail on those specifically?
It seems to be a limitation of the predictor of VJP2. Remember, it's predicting the future based on the past context. If its predictive horizon is too short, or if an event happens almost instantaneously between frames, the world model can't see it coming.
So it gets surprised by the pop.
Right, it gets surprised by the pop, but isn't surprised the very signal we're using to guide it.
Yes, but in this case, the surprise is valid. The balloon did pop. The physics was correct. But the world model interprets that high surprise signal as physics violation rather than sudden valid event.
So it penalizes the correct outcome.
Exactly. It generates a negative reward. It tries to steer the generation away from the pop because that sudden transition looks like a glitch to the latent model. It wants the balloon to stay a balloon because that's the path of least surprise.
That makes perfect sense. It's biased towards continuity, and an explosion is inherently discontinuous, so it smooths over the very event you're trying to generate. Precisely. And they also mention that complex material properties are still hit or miss, so things like mirrors, reflections, or something really complex like the siphon effect, where liquid travels up a tube. The model still struggles there.
And the reason is probably the same, right? VJJP2's training data just might not have covered enough of those niche scenarios to learn the latent rules for them.
Exactly. It's only as good as its own understanding of the world.
So we haven't solved physics entirely, but we've built a much, much better bullshit detector for it.
A detector that can actively steer the ship, yes. And I think, importantly, it proves that world models are a distinct and powerful tool separate from generative models.
So to wrap this up, the paper is Inference-time Physics Alignment of Video Generative Models with Latent World Models. It really feels like the big takeaway here is that you don't always need to retrain these massive foundation models to fix their flaws.
That is the core efficiency insight, I think. We're seeing this shift towards System 2 thinking for video. Instead of just firing off a prompt and hoping the System 1 intuition of the model gets it right, we're now using a System 2 judge the world model to deliberate, search, and refine the output at inference time.
Which brings up a really provocative thought for the future. If inference-time search can fix something as fundamental as physics, are we entering an era where that thinking time, the inference compute, becomes more valuable than the raw model size itself?
I think that's a real possibility.
Could a smaller model, if you give it a massive amount of search and a really good world model, actually outperform a giant model that's just doing greedy first-pass sampling?
I think that is exactly where the field is heading. The scaling laws might start to shift from pure parameter count to inference-time search depth. We've already seen it happening in reasoning tasks with LLMs, and now we're seeing a clear parallel in physics for video generation.
A fascinating possibility. Well, that's all the time we have for today. We highly recommend you check out the full paper, especially for those visuals of the floating ducks and dominoes. It really helps to see the difference in motion. Thanks for listening to AI Paper Podcasts.
Thanks for having me.